In this video, we'll talk about the solution to the wave equation that we derived last time. So let's first review the wave equation that we had last time. The wave equation is given by the following differential equation: partial y partial x squared equals 1 over v squared partial y partial t squared. Okay, again, it comes from the Newton's second law, and y represents the particle displacement along y-axis, and x represents the particle position and t is the usual the time. Okay, now here's the wave diagram we usually think of. Now the let's see the coordinate system. Let's say that's the x-axis, and here's the y-axis. Okay, so now we're looking at the wave source at the origin O. Okay, and O, the particle O here at origin O is going to do oscillation in y direction. So now at this moment, let's say it's moving downward. So velocity y here for point O. Okay, now if I look at another particle, let's say here, then its velocity is right now is downward because it's going to follow the earlier particles, and that's Vy. Let's call it 1. Etc. So you can draw these for all the particles along the wave propagation. So now we know at the origin here, the y expression here. Now remember the differential equation here. Y has two parameters, x and t. Okay, so y, the displacement is a function of particle position x and the time t. So we need to find out this expression. Okay, and let's think about just one point for the moment. So if x equals equals 0, which is the origin O, then we're looking at the oscillation of the wave source. And the wave source, we say its oscillation is simple harmonic oscillation. Simple harmonic motion for wave source. So that means that I can use our previous oscillation chapter's result to write it down. So I can say now x equals 0 here, and y is just a function of t, and then we can write down a cosine omega t plus y naught, right? So that's the solution that we obtained from the previous chapter. Now people usually like to write down the wave equation here using a sine function, and that is actually not a problem. So if we add another like additional phase here, let's say plus pi over 2, and we absorb that phase into this phi naught constant, then we can say y x equals 0 and t equals a sine omega t plus phi naught. Okay, but again, this phi naught is a different phi naught than the previous phi naught. And there is a sine function, right, represent these particles motion, and then all the later particles they're going to imitate the wave source by doing the same kind of simple harmonic oscillation. So you can imagine that all these, for any position, all these particles, their oscillation y, their equation form is exactly the same as this one, very similar to this one. So you can expect something to be amplitude y, a here, amplitude should be the same, and it should be a sine function. But what to include in a sine function here? Especially, how do we include x? Now, without solving this equation, we can argue in the following way: the equation, the wave equation solution is given by a certain form. So let me show you how. So first, we know the oscillation of this simple harmonic motion. It has periodicity capital T, and that is in the time direction. And to capture this periodicity in time, we define a quantity called omega, which is 2 pi over t, right? It's 2 pi over t, and we call that angular frequency. And then the effect of time is captured by multiplying omega with t, with time. Okay, so we capture the effect, or we can say we capture the contribution of time in a sine function by sine omega t. We capture it by this way. Now remember, we also have from this picture the periodicity in space. So if I look at let's say this length of the wave, and then I will keep looking to the right, the repeat of such a pattern, then I can say there's a periodicity in space, right? So every this length here, the wave is going to repeat itself in the exact same way. So that's why we call this periodicity lambda. We call it wavelength. So let me define this. Periodicity in space is defined as lambda. So now the space contribution to the sine function should be similar to the time's contribution to the sine function. So we expect something like omega t, or maybe another quantity defined with respect to lambda, and then we call that, actually let me define that first. So the periodicity in space is lambda, so we define this quantity called k. It's given by 2 pi over lambda, and this quantity is called wave number. Now, a proper understanding of this is that, so now let's say if I look at 1 meter, let's say I'm looking at let's say total length of 1 meter, and I'm asking how many wave shapes do we have here in terms of how many lambda we have here. Then I'm going to say 1 over lambda, right? So that's the wave number, the number of complete wave shapes. And that's captured by this quantity called wave number, k is 2 pi over lambda. The product of 2 pi here is simply just to account for the sine function that it needs the radian as the unit. So we need to multiply 2 pi here to account for one complete cycle. Okay, so that's why we have 2 pi here. And then its contribution to the sine function should be in a form similar to the omega t. So I'm going to say kx here. Okay, so that's why the solution, so everything now combines here to figure out the solution of the wave equation that we derived last time. The equation should have solution a sine kx and omega t, and then plus phi naught, still the initial phase that we wrote down for the simple harmonic motion. But how to combine these two, kx omega t? We could have a plus sign between them. We could also have a negative sign between them. Okay, so the positive sign will mean the wave propagation is to the left. And a negative sign will mean propagation to the right. So I will talk about these meanings later on, okay? But right now, we know there must be a combination of kx omega t. They both contribute to the phase of this function sine, the sine function, and then that phase is important, okay? So let's also define this quantity here. We call phase. So the whole thing inside the argument of sine function is called a phase. We use a phi here to represent that. So equals kx plus minus omega t plus phi naught. Okay, the whole thing again is called a phase. And that is the solution to the differential equation to this equation. Okay, now let's make a check of the solution. So I want to do some derivative here. So if I'm looking at the first derivative of y with respect to x, I get, let's see, from here I get k times a sine kx either plus or minus omega t plus phi naught. Excuse me, becomes cosine. Now the second derivative of y with respect to x now becomes, now we bring out another k here, so negative k squared a sine kx plus minus omega t plus phi naught. Now I also need to check the first derivative of y with respect to time, and then do the second derivative. So first the derivative is given by, now I'm going to bring out plus or minus omega to the front times a, and then cosine kx plus minus omega t plus phi naught. Now the second derivative with respect to time is then given by, we bring out another set of plus minus omega, and then they will cancel exactly with the sign here. So we get omega squared, but we also need to add negative sign here because they comes from the cosine becomes sine. Derivative for cosine becomes negative sign. Okay, so let's plug in the wave equation that we had earlier. So let's see, we have for the left side negative k square a sine plus minus omega t plus phi naught equals 1 over v squared negative omega squared times a and then sine. Now the sine function will cancel out. They're exactly the same, and also including the a here, they're also the same. So that leaves us this equation. So k squared equals omega squared over v squared. Okay, so I'm going to say that that is the relation that we need for the solution to be satisfied. For the solution that we write down here to be satisfied by this differential equation, we need this relation. So that's why the wave speed, now we figure out the wave speed is given by omega over k, and remember omega is 2 pi over lambda, 2 pi over t, sorry, and k is 2 pi over lambda. So we get lambda over t here as the wave speed. And also the 1 over t is frequency, is f. So we can also say lambda times f here. Okay, so that's another important relation. V equals omega over k, or V equals lambda times f, or lambda over t. And that is the condition that we need to satisfy the for this expression here, to satisfy this solution, satisfies this equation. Okay, all right. So that's the solution to the differential equation. So now let's think about the property of this wave function. The solution here is called the wave function. So y equals x and t function equals a sine kx plus minus omega t plus phi naught. Now a here again is the amplitude of the oscillation. Now k you already know is the wave number. Omega is angular frequency. Phi naught is the initial phase constant. Now, if I want to look at the how to plot this function here in a diagram, then I can do two things. First, I can say I want to fix, let's say I fix the position to some specific point, let's say x naught. Then the function here now is only a function of t, because x equals x naught. Okay, and then we get a sine kx naught now becomes a constant, plus minus omega t plus phi naught. And if I plot that, then I plot y versus time. Okay, but it's only for this point x equals x naught. So that's why we say this kind of diagram is called history diagram. And it's the diagram for one particle at x equals x naught at this particular position, and for its motion at any instant at any time t. Okay, so you can see clearly the particle's position at any instant. So let me draw a diagram to show you that. Let's say we have such a diagram. Okay, now it's only, again, remember it's only a function of time. So if I check the periodicity in this time direction, So I should read capital T here, okay, because that's the period, periodicity in the time direction. Now the amplitude is still the same. That's still the same A we have in the equation. That's the same A here. Again, it's called a history diagram. Now what happens if I fix the other variable, let's say t equals t naught, fixed it at one instant. Now the y function, it becomes a function of x only because we set t equals t naught. So we get this function here, kx plus minus omega is t naught plus phi naught. Okay, now the whole thing here becomes a constant. And this kind of diagram is called, if I plot it y versus x, then it's called snapshot. And snapshot is the diagram for all particles in a wave, not just one particle, for all particles at one instant t equals t naught. And this diagram is kind of like taking a picture of all people, and all people is frozen. Their expressions are frozen at that instant when we take the picture. So that's this kind of diagram. And plotted in the coordinate system will be like this, y versus x. And if I have, let's say, a similar diagram that look like this, then the periodicity in the in this diagram here will represent wavelength lambda. So you can read out lambda directly from the diagram. The amplitude can also be read from the diagram. It's also A here in the y direction. Okay, so let's do a little bit more with the wave function. Let's say, let's start a new page here. So y equals yxt a sine kx plus minus omega t plus y naught. So let's take a first derivative with respect to the time, partial y, partial t. Then we get negative plus minus omega times a cosine kx plus minus omega t plus y naught. Okay, now what we have here is the velocity of particle. And that's why we call it Vy, okay, because particles are oscillating in a y direction along the y-axis. So that's why we call it the velocity Vy. And that's different from the wave speed. Wave speed is V without the index y, and it's defined as omega over k or or lambda over t or lambda times f. Okay, so that's the wave speed. It's a different quantity from the wave speed, the particle speed. Now, if I take the second derivative of y with respect to time, then I get omega squared with a negative sign come from the cosine derivative becomes negative sign kx plus minus omega t plus phi naught. Okay, and that's called ay, acceleration of the particles along this direction. Okay, so one more thing here about the plus or minus sign, and previously we said that they represent the propagation direction. Okay, so now let's see why we have that. Let's start with a positive sign. And we want to do the following. So let's say we have two particles, x1 and x2. And the motion of x1 is propagated to x2 later on. Or maybe x2 propagate to x1 later on. So I want to figure out which one is earlier, and later particle follow earlier particles. Then from there we can determine the propagation direction. And I will talk about whether the sign, positive sign here, represent that or not. Okay, so let's think about the motion propagation. So the y1 must be equal to y2, and I want to use this expression. So kx1 plus omega t1 plus y0 equals a sine kx2 plus omega t2 plus y0. Now, in order for this equation to be true, we must have kx1 plus omega t1 equals kx2 plus omega t2, okay? Because the two y0 cancel out. And let's rearrange the terms. So let's say we have k x1 minus x2 now equals omega now t2 minus t1. Okay, so now let's say suppose we have such arrangement so that x1 is less than x2. Okay, so x2 is to the right side of x1, or x1 is to the left side of x2. Now if you have that, then the left side here is negative. Okay, now in order for this equation to be true, we must have t2 minus t1 also negative in order for the two displacement to be the same for the two particles. And that would mean t2 is less than t1. Okay, so let's draw a diagram. So here is the x, and x1 is less than x2. But t2 is less than t1 means t2 is earlier, right? t2 is smaller, so it's earlier. And t1 is later. So that means that the propagation of the wave is from right to left. That's the v. The wave propagation direction should be from right to left. So that means that the source is on the right side. Wave source is on the right side. Okay, and we can do the same thing for the negative sign. Again, we assume 2 points x1, x2, and then they have equal y. Okay, so let me write down the arguments of the sine function directly. And then through the rearrangement of these two terms. Okay, so now again, we assume x1 less than x2. Then we must have t1 less than t2. So t1 is earlier time, and t2 is later time. Okay, now reflect it in the diagram. So let's say that's x, x1, and x2. X1 less than x2, and then t1 is less than t2. So t1 is earlier, and t2 is later. Okay, so that means that the wave propagation is from left to right. That's the wave speed direction. Okay. All right, so that's the meaning of plus or minus sign in the wave equation. Okay, so next time we'll talk about some special wave, such as the sound wave. Okay, we'll talk about the property of sound wave. And that's all for this video. Thanks for watching.